Hi learners, welcome to the course Quantum Chemistry. In this module, we are discussing particle in 3D box problem. The contents of this module are particle in 3D box problem description, Schrodinger equation of the problem, method of separation of variables, solution of Schrodinger wave equation of particle in 3D box, wave function of the problem, expression for energy of a particle in 3D box, concept of cubical box, and finally concept of degeneracy. First of all, the particle in 3D box. We can describe the problem like this. The particle in 3D box is a simple extension of particle in 1D box problem. Consider a particle trapped in a 3D box of length, breadth and heights respectively A, B and C. This implies that the particle can travel in any direction, that is along either x, y or z axis. The potential energy inside the 3D box is 0, while the potential energy outside the box is taken as infinite. This is the pictorial representation of particle in a 3D box. This is a 3D box or simply a parallelepiped with the sides A, B and C. The length along x-axis is small a, that along y-axis is taken as small b, and that along z-axis is taken as small c. Now we have to discuss the boundary conditions of the particle in 3D box problem. From this it is clear that along the x direction, the distance is from 0, this is origin 0 to A, that is 0 less than or equal to x less than or equal to A. Along the y direction, the distance is from 0 to B, that is along the y direction 0 less than or equal to y less than or equal to B. And finally, along the z direction, the edge length is taken as C, that is 0 less than or equal to z less than or equal to C. This about the particle in a 3D box. This system can be considered as a parallelepiped and the edge lengths are A, B and C respectively. Now more about boundary conditions. The wave function psi of xy z satisfies the boundary conditions that it vanishes at all the walls of the box. Psi 0 y z equal to psi a y z equal to 0. That is, for any values of y and z, psi 0 and psi a equal to 0. Psi x 0 z equal to psi x b z equal to 0 for all values of x and z. Finally, for all values of x and y, we can designate it as psi of xy 0 equal to psi of xy c is equal to 0. This about the boundary conditions that describe the particle in 3D box problem. Now, we have to discuss the Schrodinger wave equation of the particle in 3D box problem. For a particle in 3D box problem, we can obtain the Schrodinger wave equation as follows. We have the general form of the time-independent Schrodinger wave equation. Hamiltonian psi is equal to energy into psi. It should be noted that the wave function psi depends on three variables x, y and z. Therefore, I can put psi as psi of x, y, z. For simplicity, we are taking psi as psi of x, y, z as psi and Hamiltonian psi of equal to energy into psi. This is the Schrodinger equation in general form. This is the time-independent equation and we can split it into further parts. On splitting the Hamiltonian, that is minus s cross square by 2m del square plus v into psi is equal to energy into psi. But it should be noted that the potential energy V of the particle inside the box, inside the three-dimensional box is taken as 0. Therefore, the term V vanishes out and we will get minus s cross square by 2m del square psi is equal to energy into psi, or del square psi is equal to 2m by s cross square with a negative sign into energy into psi, or del square psi plus 2m by s cross square into energy into psi is equal to 0. That is, on further simplification, we can have the complete form dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 2m by s cross square can be taken as 8 to pi square m by h square, since s cross or Dirac represents h by 2 pi. Therefore, this term can be represented as 8 to pi square m by h square into energy into psi is equal to 0. This about the Schrodinger wave equation of the particle in three-dimensional box. This is the equation that we need to solve in order to get energy and wave function of particle in a 3D box problem. Now, in order to solve the Schrodinger wave equation of the system, that is minus s cross square by 2m dou square psi by dou s square plus dou square psi by dou y square plus dou square psi by dou z square equal to energy into psi of x, y, z, we have to first separate this Schrodinger wave equation into three equations in each variables. This is because this Schrodinger wave equation as such contain three variables, and the simultaneous solution of such an equation is very difficult to obtain. So, in order to solve this, first of all, we have to separate this equation into three parts. That is, we have to use the method of separation of variables to separate this equation into three parts. We will use the method of separation of variable to solve this equation, and for adopting the method of separation of variable, first of all, we have to use this relation. That is, psi of x, y, z is a product of three components. That is, x of x into y of y into z of z. It should be noted that x of x represents the part of the wave function, the part of the total wave function which depends on variable x only. Similarly, y of y represents the part of the wave function which depends on y coordinate or y variable. Finally, z of z represents the part of the wave function which represents z coordinate or z variable. Thus, we can split psi of x, y, z into x of x, y of y and z of z. The total wave function psi of x, y, z is a product of three components, namely x of x, y of y and z of z. By using this assumption, we are going to separate three variables present in the system. And first of all, we have to substitute this function, this value, psi of x, y, z equal to x of x into y of y into z of z in this equation, and we have to separate. We can proceed separation of method of variable as follows. Thus, we get minus s cross square by 2m into 1 by x of x into d square x divided by dx square plus 1 by y of y into d square y divided by dy square plus 1 by z of z into d square z divided by dz square equal to ex plus ey plus ez. Here, ex, ey and ez represents three components of energy. LHS equal to a differential term and RHS equal to sum of three energy term. We can split each terms like this. Equating the parts of x, we are getting minus s cross square by 2m into 1 by x of x into d square x divided by dx square equal to ex minus s cross square by 2m into 1 by y of I into d square y divided by dy square equal to energy along y direction, and finally minus s cross square by 2m into 1 by z of z into d square z divided by dz square equal to energy into z. Thus, we get three equations. Each of these equations contain only one variable. In the first equation, x is the variable. In the second equation, y is the variable. And in the final equation, z is the variable. That means we got the three relations, each equation being only one variable in it. Now, we got to three equations after the separation of variables, and they are like this, where ex, ey and ez are constants, and ex plus ey plus ez is equal to total energy of the system. Now, solution of the three equations. We have to apply boundary conditions to solve the equations. On applying the boundary conditions, that is, for example, the boundary condition along x direction is 0 less than or equal to x less than or equal to a, and solve the x equation, we are getting x of x equal to ax into sin n pi by a into x. For convenience, n is just put as nx, where nx is the quantum number that along x direction, and it can have values 1, 2, 3, etc. Similarly, to solve the y equation, we have to apply the boundary condition along y direction. The boundary condition along y direction is that 0 less than or equal to y less than or equal to b. On applying that, we are getting the solution to the y equation, that is y of y equal to ay sin ny pi y divided by small b. Here again, ny represents the quantum number along y direction, that is equal to ny equal to 1, 2, 3, etc. Similarly, if we are applying the boundary condition along z direction, we are getting the solution to z equation as z of z is equal to az into sin nz pi z divided by c, where c is the edge length along z direction, and the boundary condition along the z direction is 0 less than or equal to z less than or equal to c. This about the three solutions of three one variable equations. X of x, y of y, and z of z values are like this. Here in these three equations, we are having three quantum numbers, namely nx, the quantum number along x direction, ny and nz, respectively the quantum numbers along y and z directions. And it should be noted that the constants ax, ay and az are the normalization constants. Hence, the solution represented here are non-normalized solutions or non-normalized wave functions, and on normalization of these wave functions, we will get to the normalized wave function by incorporating the normalization constants ax, ay and az. Now, the complete wave function. We already learned the fact that x of x into y of y into z of z is equal to psi of xy z. This is a substitution we already made before the method of separation of variables. And when it is reverted back, we will get to the total wave function psi of xy z by taking the product of x of x, y of y and z of z. We already got to the value for x of x, y of y and z of z. Now, putting these three parameters together in a product, we are getting the total wave function of the system as psi of xy z is equal to ax into ay into az. Here three normalization constant I put it together. Then sin nx pi x by a, sin ny pi y by b, and sin nz pi z by c, and also ax, ay and az are the normalization constant which can be evaluated through the procedure of normalization. Now, we have to get the normalized wave function. So, we have to normalize the wave function. For the procedure of normalization, we already learned it, integral psi star rt, psi of rt, d tau must be equal to unity. And it is applied to the present system, we are having this relation, integral 0 to a dx, 0 to b dy, and 0 to c dz, psi star xyz, psi of xyz is equal to 1. And on applying this and on solving this by substituting the values, we are getting the final solution as psi of xyz or psi of nx ny nz equal to under root a2 by abc sin nx pi x by a into sin ny pi y by b into sin nz pi z by c, where nx equal to 1, 2, 3, etc. Similarly, ny and nz also have whole number values from 1, 2, 3, etc. And the products of three normalization constants, that is ax, ay and az, that is equal to 8 by abc the whole raised to 1 by 2 or under root a2 by abc. And separately, if you are taking ax, we are getting ax is equal to root of 2 by a. And if you are taking ay, we are getting root of 2 by b. And az is equal to root of 2 by c. So if you are taking the product of ax, ay and az, we will get a2 by a into b into c under root, that is root of a2 by abc. Therefore, three normalization constants I put here, and this about the complete normalized wave function for a particle in a 3D box problem. Now, we have to move to expression for energy. The expression for energy in a is a three-dimensional extension of a particle in 1D box problem. In the case of the particle in 1D box problem, we simply learned the fact that energy n is equal to n square h square divided by 8ma square, where a represents the distance along x direction. En is equal to n square h square divided by 8ma square. For simplicity, I am taking Enx equal to nx square h square by 8ma square, that is for x direction. If it is extended to the y direction, I will getEny is equal to ny square h square divided by 8mb square, where b is the edge length along y direction. Similarly, for the z direction, energy Nz is equal to Nz square h square divided by 8mc square. These are the three components of energy, Nx, Ny and Enz. We already learned the relation that total energy is equal to Ex plus Ey plus Ez. Ex is Nx, Ey is Ny and Ez is Enz. Therefore, by adding these three terms together, we will get the complete energy, the total energy of a particle in a 3D box. On adding this, here in all the three expressions, h by 8, h square by 8m is a constant, and that can be taken outside the bracket, and energy total or Enx, Ny, Nz equal to, we have to add these three terms together and taking common factor h square by 8m. Thus the total energy of the system Enx, Ny, Nz equal to h square by 8m into nx square by a square plus ny square by b square plus nz square by c square. As we know, nx, ny, nz have whole number values beginning from 1, and this represents the total energy of a particle in a 3D box problem. Energy of a particle in a cubical box. An interesting feature of a particle in a 3D box occur when the sides of the box are equal. That means we have the energy expression. We already learned the energy expression Enx, Ny nz equal to h square divided by 8m into nx square by a square plus ny square by b square plus nz square by c square. And here the edge lengths are different because our system here is a parallel pipette. That means a not equal to b not equal to c. Now we are considering particle in a cubical box problem. How the cubical geometry, the change of geometry from parallel pipette to cube affect the energy value, affect the energy expression. We are checking that. For a cube, we know all the three edge lengths are same. That is a equal to b equal to c. Putting a equal to b equal to c, both are taken as a and that a can be taken outside. Therefore, for a cube, E nx ny nz equal to h square by 8m a square. Listen the fact that a equal to b equal to c equal to a. Therefore, that a or a square can be taken outside. Therefore, h square by 8m a square is outside the bracket multiplied with nx square plus ny square plus nz square. This represents energy of a cube, energy of a particle present in a cube. Energy of a particle present in a cube is given by the expression energy nx ny nz equal to h square by 8m a square into nx square plus ny square plus nz square. For convenience, you can also replace a with the small l as the edge length or capital L or any notation can be used. Here we are taking a for simple convenience, and this is the expression for energy of a particle in a cubical box. Now, in the cubical box problem, there occur the concept of degeneracy. What do you mean by the term degeneracy? The term degeneracy represents more than one arrangement, existence of more than one arrangement with the same energy. That is, there are more than one arrangements, but the energy of each and every arrangement will be the same. For instance, p orbitals are said to be triply degenerate. That is, px, py and pz are the three possible arrangements. Each arrangement have the same energy. D orbitals are said to be fivefold degenerate, so and so. That is, degeneracy represents more than one arrangement with the same energy. For a cubical box, it should be noted that the energy of the system depends on three quantum numbers. What are the three quantum numbers? They are nx, ny and nz. This is because the total energy of a particle present in a cube is given by the expression E nx ny nz is equal to h square by 8m square into nx square plus ny square plus nz square. And by putting different values for nx, ny and nz, we can see that some of the energy levels, not all the levels, some of the energy levels have more than one possible arrangement with the same energy. That means some of the energy levels of particle in a cubical box are degenerate. We can exemplify that by taking some example. For instance, we can take one energy level associated with particle in 1D box, particle in 3D box problem. And prior to entering into the concept of degeneracy, we have to once again look into the equation of particle in a 3D box problem, particle in a cubical box problem. That is, energy is given by E nx, ny, nz is given by h square divided by 8ma square multiplied with nx square plus ny square plus nz square. Nx square plus ny square plus nz square. Now, in order to illustrate the degeneracy concept in particle in a cubical problem, I am simply taking the energy level 6h square divided by 8ma square of a particle in a cubical box problem. We are considering this energy level, and this energy level is related to three quantum numbers nx, ny and nz. By comparing the right hand side of these two, the energy value is equal to 6h square by 8my square. That is equal to h square by 8my square into nx square plus ny square plus nz square. From this it is clear that 6 equal to nx square plus ny square plus nz square. The probable chance is this one, 1 and 2. If you are taking nx equal to 1, ny equal to 1 and nz equal to 1, then 1 square plus 2 square, that is equal to 6. Hence, if I am putting three quantum numbers as 1 and 2, I will get total energy 6h square divided by 8mi square. Now, we can look on the possible arrangements. The total energy is E is equal to 6h square by 8ma square. The possible values of the quantum numbers are 1 and 2. Therefore, the degeneracy will be like this. Nx, ny and nz are the quantum numbers. I can put nx equal to 1, ny equal to 1 and nz is equal to 2. Then the energy will be 6h square by 8ma square. If I replace the quantum numbers mutually, then if I am putting like this 1, 2, 1, that is nx equal to 1, ny equal to 2 and nz equal to 1, again I will get the energy 6h square divided by 8ma square. And as a last chance, 2, 1, 1 is another arrangement. This arrangement will also leads to same energy 6h square divided by 8ma square. This means the energy level 6h square by 8ma square describes three possible arrangements based on quantum numbers nx, ny and nz. The three possible arrangements are 1, 1, 2, 1, 2, 1 and 2, 1, 1. That means the energy level 6h square divided by 8ma square is said to be threefold degenerate, or the level is triply degenerate. The level is triply degenerate. Now we can also take the energy level 3h square by 8ma square and also try to evaluate its degeneracy. See, by looking 3h square by 8ma square and comparing with h square by 8ma square into n square plus ny square plus nz square, we will get the relation n square plus ny square plus nz square, that is equal to 3. And that is only possible for this arrangement nx equal to 1, ny equal to 1 and nz also equal to 1. Therefore, nx square plus ny square plus nz square, that is 1 square plus 1 square plus 1 square. That level is having only one possible arrangement. Since all the quantum numbers are same, there is no more further arrangement possible. That means this arrangement 3h square by 8ma square, the one and only possibility is 1, 1, 1 value for nx, ny and nz, and hence this energy level is the ground state energy level of a particle in a 3D box problem. And this energy level is said to be non-degenerate. I previously mentioned that not all the energy levels of 3D box are degenerate, some levels are degenerate. We already proved that the energy level 6h square by 8ma square is degenerate. But the ground level 3h square divided by 8ma square is also degenerate. We can check for different energy levels for their degeneracy, and we can enjoy the concept of degeneracy with respect to different energy levels. Now, this pictorial representation represents different degeneracies associated with different energy levels of a particle in a cubical box problem. See, the energy level 3h square by 8m square is said to be non-degenerate, and the one and only possible arrangement is 1 on 1. We already proved that. And the second level, that is 6h square by 8m square, is said to be triply degenerate with these three arrangements. So degeneracy is equal to 3. And now consider another level 9h square divided by 8m square. These are the three possible arrangements for the quantum numbers 2 to 1, 2 on 2, 1 to 2. Here also degeneracy is 3. And for the level 11h square divided by 8m square, we can prove that 311, 131, 113 are the three possible arrangements. Hence, it is clear that some of the energy levels of particle in 3D box, especially cubical box, are degenerate. See, this level 12h square divided by 8m square is non-degenerate because only one possible arrangement is 2 to 2. So, not all, but most of the energy levels of particle in 3D box are said to be degenerate. Particle in cubical box are said to be degenerate. Now, moving on to a numerical problem. Here, this is a problem to find out the ground state energy in electron volt of an electron confined in a cubical box with edge length equal to 0.1 nanometer. And we know the energy expression for a cubical box ENX/NYNZ, that is equal to h square divided by 8m a square into nx square plus ny square plus nz square. And for the ground level, nx equal to 1, ny equal to 1, and nz equal to 1. So this energy expression will be 3h square divided by 8m a square. Substituting different values to get the energy values like this. Energy E111, that is the ground state. Nx1, ny1 and nz also 1, equal to 3 into h value 6.626 into 10 raised to minus 34 joule second, the whole square, divided by 8 into mass of electron 9.1 into 10 raised to minus 31 kilogram into edge length 0.1 into 10 raised to minus 9 meter, that is a square is needed. Since this energy is, we are getting it in joules, we have to change it into electron volt by simply dividing with 1.602 into 10 raised to minus 19. This is because 1 electron volt equal to 1.602 into 10 raised to minus 19 joules. On proper simplification, we are getting the final energy value, that is equal to 114 electron volt. That is energy of a particle in a cubical box in the ground state with edge length 0.1 nanometer is equal to 114 electron volt. Thus, in this module, we have completely discussed about a particle in a 3D box problem, obtain expression for wavelength, obtain expression for energy, wave function, and solved problems for finding out the degeneracy. That's all about this presentation. Thank you.